Here a new topic, which is a continuation of chapter 8. The topic is about flow measurement. I am still talking about internal flow, and I'm still in chapter 8, but this is a new topic, which is section 8-8 from your book, which is flow rate measurement. Let me start with easy question. Why is it important to measure flow rates of fluid? Why are we interested in measuring flow rates? This is the first question. The second question, how will you measure the flow rate of water through a garden hose? Suppose you are in your garden and you are just trying to water the flowers or whatever, and you want to know what is the water or the flow rate of water. How will you measure it? So let me first answer the first question. Why is it important to measure flow rates of fluids? Because you cannot control it if you don't know how much water, for example, or any fluid is flowing. And suppose you have a tank and you want to fill this tank with a fluid, with water or gasoline. If you don't know the flow rate, then there might be an overflow, or you are not getting the quantity of the fluid that you do want. And for the answering the second question, how will you measure the flow rate of water through a garden hose? How do you think we will do this? So let us look at this slide. So I can collect the water in a bucket of known volume. So this is, for example, this is the garden hose, and you bring a bucket, and you know the volume of this bucket, maybe 5 liters. Let us say 5 liters, 6 liters. And then you have a stopwatch. So you collect those 5 liters in a certain time, let us say 1 minute. So then you can say the volumetric flow rate is 5 liters, for example, per minute. So this is the simplest method of measuring flow rate. Just collect a known volume in a known time, and volume by time will give you volumetric flow rate. So by collecting the water in a bucket of known volume and dividing the amount collected by the collection time. So in this section, we discuss devices that are commonly used to measure flow rate. So this is the main objective in this section. We want to talk about devices to measure flow rate. Here there is an image, a figure of a man who's trying to do something. What do you think he is trying to do? He is sitting somewhere. So this is like a river, and he has this straw in his hand, and the river is flowing in this direction, and he is sitting, this straw, which is open from here, facing the direction or facing the flow direction of the water. So what do you think this man is doing? And you can see there is a level here of the fluid or the water. What do you think he's doing? So this is what he's saying to himself. As expected, whenever the tube faces into the flow, so the tube faces into the flow, water in the tube goes up. So the water in the tube goes up. From its height, from this height, okay, the flow velocity can be computed. So it seems I can know what is the velocity of the fluid by knowing this height, and you shouldn't be surprised about this. Okay, we shouldn't be surprised about this thing. Who is this scientist? His name is Pitot, okay, and he is a French scientist. And the famous Pitot tube was announced in 1732 as a device to measure flow velocity, and the Pitot tube was, let us say, was called after him, or was named after him. So what is this Pitot tube? I remember that we talked about this Pitot tube before, the internal flow, where I think we're talking about examples regarding the Bernoulli principle or the Bernoulli equation. So what is the Pitot tube? It is called Pitot tube or Pitot probe. It is just a pipe that is open from one side, and it is facing the flow. You can think of it like this. This is the pipe. The fluid is flowing this direction. Then I insert this probe like that, facing the fluid. Okay, and then the fluid is going to go inside, filling this tube till a certain height. Okay, till a certain height. And once the tube is filled, then the fluid that is coming later cannot go inside anymore because it is full. So the fluid will just stop here. Let me just change the color. Let us say this is the green. So the fluid that is coming later, it cannot go inside because it is full of the fluid, okay, of the previous fluid. So it will stop here. And because the fluid is stopping here, it is called, this fluid is stagnant. Stagnant يعني ثابت ما يتحرك, okay? And this point is called stagnation, as is written there, stagnation point. Stagnation point means the fluid is not moving, it is stagnant. And actually the pressure which is related to this point is called stagnation pressure. So the velocity at this point, so V is equal to 0, and pressure is called, or it is equal to the stagnation pressure. And I have here, this is what is written here, to stagnation pressure meter. So this is connected to a meter that will measure the pressure. Or, as you can see, I can just have the head, and I can relate head into pressure, because you know that P is equal to rho GH. So I can link pressure with head. So this is called Pitot probe. It consists of a tube that has an opening facing the flow, and from the head I can read, for example, the stagnation pressure. Now this is another type, or this is an enhancement, تطوير حق البيتو probe. This is called pitot-static probe. Pitot-static probe. Why it is called like that? Because now it is not just measuring the stagnation pressure, it is measuring two types of pressures. It is measuring the stagnation pressure, as in the Pitot probe, and also it is measuring the static pressure. So the Pitot static probe, it measures the stagnation pressure and the static pressure. How it can do this? I mean, it can measure the stagnation pressure similar to the first one, because it has this opening at the center. Let me just change the color here. Okay, so it has the opening at the center as the Pitot probe, and then it has like a layer around it, so it is like two tubes in one. So I have this at the center, the Pitot probe, and then there is another layer. Let me just show it to you in another color. So then there is another layer like that. Okay, so another layer like this, but there are holes here. There is holes, so those holes are around it, okay, around the circumference. So there's a hole here, there's a hole here, there's a hole here, but it is in the other layer. So as you can see, so there is a fluid going at the center, and there's a fluid going there around it, around the circumference. So actually I am measuring two pressures. Let me just go back again. Suppose the fluid is this green one, so there is a fluid going at the center, and this is, as you can see, to the stagnation pressure meter, and then the same fluid, but now it is going through this let us say holes, and they don't mix. This fluid doesn't mix with the other fluid, so this one is going to static pressure meter. So by doing this, now I have two types of pressure. I'm measuring two types. I am measuring the stagnation pressure here at the tip of the Pitot probe, and I'm measuring the static pressure here at these points. So let me just go through this slide with you. Let me read it with you. I just want to change the color. So Pitot static probe has both a stagnation pressure tab and several circumferential static pressure tabs. So there is one stagnation pressure, and there are a lot of those, as you can see here. See it? So this is for the stagnation pressure, and I have many at the other side also, many holes to measure the static pressure using those tabs, and it measures both stagnation and static pressures. Okay, but the question that will jump to your mind now, why do we care about pressure? We want to measure flow rate. I mean, the topic of this talk is how to measure flow rate. And from the beginning, I'm talking about stagnation pressure, static pressure. So what's the relation? How can I connect pressure with flow rate or velocity? So as you can see, this is another image or figure where you can see that the flow is coming this direction. Then there is stagnation pressure here at the tip. There is static pressure here on the sides. And then this is connected to a device. It can give you, for example, P stagnation pressure and static pressure by themselves. Or I can get this one, P1 minus P2, which is the stagnation pressure minus static pressure. So the Pitot static probe measures local velocity. It measures local velocity. Why do we say local velocity? Because it measures the velocity at a point. As you can see, I can move this Pitot static probe. I can move it in the pipe. I can put it at, suppose this is the pipe. So I can put it at the center of the pipe. For example, if this is the center of the pipe, I can move it up, I can move it down. So this is why we said it measures local velocity. It measures the velocity at a point. By measuring the pressure difference in conjunction with the Bernoulli equation. So here a suggestion. So we can use the Bernoulli equation to link pressure with velocity. We can do this. How can we do it? So this is the Bernoulli equation. You remember it from, I believe, chapter 5. So you know what are the assumptions of the Bernoulli equation. So here is the pressure head, the velocity head, the potential head. So at one point equal to the pressure or the head at the second point. So I'm just saying that the head at this point is the same as the head at this point. Okay. Why is that? I am just neglecting the losses between these 2 points, and this is a small piece of equipment. Let me go back. So as you can see, this is a small distance. There are no pumps, etc., etc. So all of the assumptions that we talked about before can be applied between these 2 points. So by doing this, as you can see, I want to get what? My main objective is to get velocity. They are on the same elevation, so I can cancel Z1 and Z2. And we said that V1, so this is point 1, so this is point 1, and this is point 2. So we said I have here stagnation point, which means the velocity equal to 0. So V1 is equal to 0. So what's left? I have pressures, and I have V2. So I can solve for the velocity at point 2, and by doing this, I can get an equation, which is this equation. So V is equal to 2P1 minus P2 divided by rho. And this V, طبعا, is the velocity here at point 2. Okay, the velocity at point 2. So as you can see that by just knowing the pressure difference and knowing the density of the fluid, I can get the velocity at a point. This is local velocity. Why? Because I can move this, let us say, Pitot static probe and then like up and down and get the velocity. So the question is, what is good about Pitot tube? What is good about the Pitot tube or Pitot probe? So the good thing about it is simple, it is inexpensive. As you can see, it's just a metal, small piece of metal, and highly reliable device since it has no moving parts. Usually when you don't have a lot of moving parts, this means it is easy to be maintained. سهل الصيانة مالته. Okay. It also causes very small pressure drop and usually doesn't disturb the flow that much. I mean, since I don't cause a lot of pressure drop, this means I'm not disturbing the flow. So those are good things. Those things are good about the Pitot probe. So let me summarize this short lecture. In this lecture, we talked about why it is important to measure flow rate. We talked about the simplest method to measure the flow rate, which is just collecting a known volume through a known time. Okay, and then we talked about the first device to measure the flow rate, which is called Pitot probe. It is named after the French civil engineer Henri de Pitot. And we said we can do this by measuring the pressure at 2 points, the stagnation point and the static point. So we can have the difference between the stagnation pressure and the static pressure. And then we can link the pressure difference with the velocity. طبعا if we know the velocity, بعدين ايش اسوي اذا flow rate? If I know the velocity, I can just multiply the velocity by the area. This will give me the volumetric flow rate. If I can take the volumetric flow rate and multiply it by the density of the fluid, I can get the mass flow rate, and this will solve our problem by looking for the mass flow rate or volumetric flow rate.